I'm not going to. So, now I want to bring together a couple of things from our last two examples. Okay, the thing I want to bring together is I wrote the equation for current in terms of voltage. I wrote both of the equations on the board. Okay, now the big question here is why are they different? We have the same exact components. The same exact components. But the current equations are different. Okay, here, for our first configuration, where everything was, oh my goodness, look at how great that is. Oh. Oh, it shows up great on camera too. For our first equation in series, where all the components were in series, the equation is 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 equal to VS times 1 over R1, R2, R3. Sorry, those are added together. Plus. Okay, for 2 in parallel, IS is equal to VS times 1 over, whoop. Yep, sorry. There is a huge difference between them. To somebody who is novice at algebra, can't those just be combined to be the same thing? Well, they can't. They're not the same. They have the same units, because in each time it's voltage divided by resistance. But these are distinctly different. R1 plus R2 plus R3. R1 was 60 ohms. R2 was 40 ohms. R3 is 20 ohms, okay? This number here, when we calculate it, is equal to 1 over 120. This number here, when we calculate it, is equal to 1 over 60 plus 1 over 40 plus 1 over 20. What does that equal to? I'm not doing that one in my head. Sal? I'm just kidding. Somebody help me out here with a calculator. I will do this on my phone and I don't like it, so. .091. What is 1 divided by 120? Just by comparison. Yeah. 1 divided by 120. 0.08? And why are these numbers so different? Because series and parallel are different configurations, okay? If you combine components in parallel, the power consumption for the entire circuit will be higher. Why? Because in a voltage source, they're all going to be at the same voltage. Adding a resistor does not change the voltage of the other components. It doesn't change the current of the other components. When you have a voltage source here, and we take one component, okay? We did this at the beginning of class. We can figure out what the current is traveling through that component. Guess what? That current doesn't change. That current doesn't change. That way, if you look around the computer, you still can't see it. Yeah. That current doesn't change if we tack on another one. The current through this one stays the same. Why? Because it still has the same voltage across that component. Still has the same resistance. The current is going to stay the same. The power consumed by this element does not change when we add another one in parallel. But, as we pointed out in the last example, the power consumed by the battery has to increase because the total power consumed by the circuit is equal to the power that's given to the circuit by the battery. So, adding components in parallel is going to increase power consumption when you have a voltage DC source. Now I specify voltage DC source because it's actually not true for a DC current source. The relationship is flipped on the other side. So if I keep adding components to this voltage source, we will continue to see increased power consumption out of it. All of these lights are connected in parallel for that reason. LED lights are connected mostly in parallel. You usually have strips where they're connected in series, but it's for this reason. You can have an entire strip of lights, and the power consumption from the battery will change. You just add another light. But everyone is going to see the same amount of power going to every element, depending on how many lights are in that series. It doesn't change anything. Okay? When we change to a series configuration, okay, if I were to go back to this equation, and we'll take out R3 entirely, so it's just R1 plus R2. Instead of having 120 ohms, it now becomes 100, which means this does change both the current and the voltage applied to every member. Adding another member in series reduces the total amount of current traveling through the system. It's increasing resistance. Be like, okay, it snowed recently, so that's a great example. Let's say you have people that need to go out and drive in the streets. Well, the more snow, the more resistance to driving, the fewer people you're going to see out on the streets, in theory. Or the more people you're going to see out there on the streets who have abandoned their cars, depending on how you look at it. But in the same case, the more resistance, the less current, the less traffic, the less flow. If we add more resistance in series, it changes the entire resistance of everything the battery sees. And so when it comes down to it, what we really need to look at is, what is the battery looking at? Okay, when we looked at just, what I told you at the beginning of class is I can give you the voltage source voltage, but I can't give you the voltage source current until I do the math of the system. The reason for that is because the current is dictated by how the system behaves. As we did two different calculations, we found two different current values. Okay? It's driven by the system. Voltage applied is constant because that's what the power supply gives. The current is then driven, or the other way around. If the current is applied, the voltage is driven. One of those characteristics is driven, so it's important for us to be able to do this and figure out what is it that the battery is looking at. Okay? All of these are in parallel. All of these are in series. Turns out we can combine them. And we can combine them using the equations that we wrote up here. All right? This is the concept of an equivalent resistance. A battery will behave identically to this system as it would to this system that has a, what? What is 1 over this value? This one. It should be something like 12. 1 over 0.091. 10.9, that was close. I'll just write 11. Okay? The battery behaves identically. We plug in a battery. It doesn't matter what battery we plug in. that battery is going to behave identically if plugged into these two circuits. As far as the battery is concerned, looking out into the circuit, these two are identical. This brings about the idea of what is an equivalent resistance. An equivalent resistance is basically if you're the battery and you're looking out at the circuit and trying to figure out how much current to supply, you're going to be able to figure that out, and you'll give as much current no matter what that resistance is because it's an equivalent resistance. Okay? As long as whatever to the right of this comes to an equivalent resistance of 11 ohms, your battery will be the same. Nothing else matters. It doesn't matter if you have components in parallel series. It doesn't matter if your system is so large it spans this board. As long as the equivalent resistance comes back to 11, they're identical as far as the battery is concerned. Okay? And that allows us to simplify the circuit significantly. Equivalent resistances, let us take this one and calculate it as if it was one resistor. Here, these add up 60, 40, 20. Well, nope, sorry. These add up to 1 over 120. The equivalent resistance here is 120 ohms, which means a battery plugged into a single resistor with a resistance of 120 ohms, the battery behaves the same. These two systems are functionally equivalent. We'll draw the battery back in. Doesn't matter what the battery is. Battery is irrelevant. As long as the battery is the same between the two, those two systems behave identically. You can take these resistors and you can imagine that they're just one resistor that just happens to have a couple wires stuck between them. Okay? That's it. And if we do it that way, it simplifies our math. Because the problems I'm going to give you, probably won't get to them today. Problems I'm going to give you are going to start getting really ugly intentionally. And we're going to have to really, we're going to have to punch through some hard math right now. Because these concepts are not intuitive. The idea that we can look at 3 components and then we can look at 1 component and we can say 3 equals 1. And then how does 1 equal 3? It's a little off. But we're going to have to do that for a system. So the equation is in series. Equivalent resistance is equal to R1 plus R2 plus R3 plus ... Okay? When components are in series, you can simply add them and come up with one single resistor that is equivalent. In parallel, that changes. Your R equivalent is 1 divided by 1 over R1 plus 1 over R2 plus 1 over R3 plus ... And this should have been in your reading. It's foundational to understanding resistance. Okay? And again, the goal here is we're taking this system and we're simplifying it so that we can understand what the battery is doing. Because if we understand what the battery is doing, we can then step back into the system and figure out what the system is doing. The battery depends on the system depends on the battery. It's a whole convoluted mess. Circuits are not intuitive. This is why this is a challenge. Okay? And it should be a challenge. It's okay to look at this and go, what the heck, Kale? I thought we were cool. And then you're wrong, because we're not, because now I'm torturing you with math. Okay? All right. I have like 8 minutes. I'm going to do a quick problem. So knowing equivalent resistances, it allows us to combine resistors to make simpler problems. So what happens when I have a system that looks like this? Just run. I gave this one to you already today. I'm gonna make this easy. Every one of these is 10 ohms. Okay, we'll go ahead and label our nodes. And the question that I want to ask here is, what is the power going through R4? An ugly question to ask, but I do it on what? Thank you. We'll say Vs is also equal to 10 volts. Everything is tens. Decimal system is kind. Thank you, Mr. Decimal. All right. We can write out all of our KVL, KCL equations. That's fine. Those are all true. Everything exists. We can actually solve this entire system using KVL and KCL. That is also fine. That is also true. Now that we have 2 new equations in our arsenal, which I've erased part of one of them, we're going to go ahead and use this a little bit before we jump into giant massive equations. Okay? Because it'll give us a little bit of insight into how the system is working. So, goal here, figure stuff out. I'm going to go ahead and find an equivalent resistance first. Yeah, you can do the KVL, KCL method. That's actually called node, it's a combination of mesh current analysis and node voltage analysis, which is another part of the book that we're not going to cover because I don't like separating those two values, but I'll cover a little bit of node voltage analysis, but not today. I don't want to get into matrices. None of you guys have learned matrices as far as I know. Anybody learned matrices? Didn't think so, yeah. Matrices are a different fun kind of math. So we're going to go ahead and take this. Now we know if I draw out my graph, I'm going to put this in the hardest place for Sal to see.
Oh, you're fine. You can move.
You could move.
And I will.
This computer cannot move. Okay. I can move this cart.
Yeah, we're going to the religion.
That would be a me move. It really would. I'm awful. Okay, we're going to create a chart, and this chart is going to be inputs, output. We got 4 resistances. We already put this chart up once. R1, R2, R3, R4. What is the input to R1? What node feeds the input to R1? Comes from 1. Sorry, I saw you did a hand sign. I couldn't tell if you were flipping me off. Hey, we all woke up early this morning. It happens. Okay, so the input is 1. What is the output? It's 2. Okay, input to 2 is, it's 2. So node 2 feeds into to R2, and then it comes out at node 3. Okay, R3 comes into it. At this point, I'm just looking at you, so. Okay, and goes out at 4. And this is the same for R4. Comes in at 3, goes out at 4, okay? What we identified at the beginning of class is that these two are in series, these two are in parallel, and these two are in series with this combination in parallel. All right? So as we go to do equivalent resistance, the first thing I'm going to do is I'm going to take this system and I'm going to get rid of the easy ones. Okay, we can combine these two because there's one input, one output here at node 2. We know those two are in series. We can go ahead and combine those. So we'll go ahead and say REQ1 is equal to R1 plus R2. Why is it R1 plus R2? Because they're in series. Okay? And so that's going to be equal to 10 plus 10, which is equal to 20 ohms. Okay? And we're going to go ahead and say these two now are REQ2. And that's going to be equal to 1 over 1 over 10 plus 1 over 10, which 1 over 10 plus 1 over 10 is 1 over 5, which is 5 ohms. Okay? So when we took this system and we took these two equivalent resistances, we're saying this system behaves identically to this system. Where we're using equivalent resistance 1 and equivalent resistance 2. We did the easy math. Okay? Now we can rewrite all of our nodes. Node 1 and 4 haven't changed. They're on this side of the battery. This over here is no longer node 2, and this is now node 3. Because when we combined these two, we combined them across 3 and 4, where 3 is the input, 4 is the output. When we combine these two, we combined them with node 2. We're assuming node 2 is inside of REQ1. So I can go ahead and draw 2 in there. It's right in the middle of our REQ1. Okay? Well, we can take this system and make it simpler still. REQ1 and REQ2. Are they in series or parallel? Let's go ahead and write out our chart. Okay? This is a new chart. So we have input, output. Okay, what is the input to REQ1? What node feeds in? It's 1. What node takes the output of REQ1? It's 3. So it starts at 1, ends at 3. What node feeds into REQ2? It's also 3. Guess I should. Okay, what node is the output of REQ2? It's 4. Okay? 1, 3, 3, 4, those are in series. They're not in parallel because if they were in parallel, they would both be starting and ending at the same number. This starts at a number, ends at a number. This starts at the number this ends at. And there are no other components that start at 3 because we made an equivalent circuit. Okay? We can now take this and say, okay, these are in series, which means REQ3 is equal to REQ1 plus REQ2. And the reason why we did that is because we're using the series equivalent resistance equation, which I am now going to erase. Okay, so our series equivalent resistance is 20 plus 5 equals 25 ohms, which means the total system equivalence, the battery behaves the same here and here. You have node 1, you have node 4, this is REQ. I'm not even writing letters anymore. REQ3, if we put a 25 ohm resistor here across the terminals of the battery, it would behave identically to building this entire circuit. The battery would. Which means we can figure out what the current is coming out of the battery. I'm out of time. I am going to keep teaching. You can leave. I'm going to record this. This will be on YouTube. If you need to go, I need to finish this example. I don't want to start this in the next class. Okay? So, if you need to leave, I don't know if I can pause the stream for a little bit. Maybe, maybe not. I don't know. But if you need to go, this will be on YouTube. You should come back and watch the end of this. But I'm going to do this right now. See you Tuesday.
See you later.
See you Tuesday. Okay. So I'll finish this quickly so you guys don't have to watch this on YouTube. The idea is power coming out of this is going to be equal. Everything is going to be equal. The power consumed, the current coming out of the battery, the voltage across the battery, everything is the same between this circuit and this circuit. 1 and 4 have not changed. Everything that happens between 1 and 4, the voltage difference, the current between them has not changed. It's all the same. And we can plug in one resistor here and figure out what that is. And this is much easier because this is 25. So we have a 10 volt source voltage and we have a 25 ohm resistance. What is the current coming out of the battery? Well, if we do our KVL, KCL for this system, we have one loop. We know that Vs is equal to VREQ 3. Okay, we have two nodes. Both of those nodes come up with the same equation, and that equation is 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 equal to IREQ 3, and then IREQ 3 is equal to IS. Same. Okay, well, we know that there are, we also know we have our component equation. We have 1. And that is VREQ 3 is equal to IREQ 3 times REQ 3. Okay. Well, so we know that VS is equal to VREQ 3. We know this is 10. We know that the currents are equal. So if we solve for the current that's going through IREQ3, we can find the current coming out of the battery. We didn't need to solve all of those other components. Now I asked you specifically for power in R4 because it does make it harder. This method is very simple for figuring out what the battery sees, and it's necessary when we talk about Thevenin and Norton equivalence in the next class. This is critical to understand, just how to combine resistances to all be equal. But at the end of the day, you still have to step back out to figure out what the voltage is across R4. But this can give us a good insight as to what each of these are. Okay, so with all of this fun math jazz, just started further on the board. We can take these equations, take REQ3, take this one right here. We know this is 10, we know this is 25. So IREQ3 is equal to VREQ3 divided by REQ3, which is equal to 10 over 25, which this current value is going to be equal to 0.4. Maybe.
Yep.
Yes? Yes!
Did you know one you had?
Yes, I did. Okay, so there are 0.4 amps coming out of the battery. And now we know that definitively. It doesn't matter what goes on in the rest of the circuit. We know that there are 0.4 amps coming out of the battery. Are there 0.4 amps that are going to be going through R4? That's a no. Why not? Because the current going into R3, because these two are in parallel, the current actually splits. So the current going through R4 and R3 are going to add to 0.4. The current going through R2 is equal to 0.4. Current going through 1 is equal to 0.4. We can do KCL and KVL and figure that out. There's just 1 in, 1 out, 1 in, 1 out. So this is all going to be the same. They're all in series. Series components all have the same current. So we know these three are all at 0.4. If we step back to this circuit, REQ1, we know there's 0.4 amps going through this. If we were to replace R3 and R4 with an equivalent resistance, there would be 0.4 amps going through that. Because we know there's 0.4 amps going through this system. 10 volts, 0.4 amps. Nothing has changed because we looked at the equivalent resistance. We know what the behavior is of the battery. And knowing what that current value is of the battery means we can now plug that in other places and get a better answer. So here we know this is 0.4 amps, okay? Which means there are 0.4 amps going through here, which means there's 0.4 amps going through here. With 0.4 amps going through REQ2, what that says is that REQ2 extends between 3 and 4. Okay? If we did KCL on the second equation, we know that those equations are true. Okay, I'm speeding this up a little bit because I'm trying to get you guys out of here. I didn't want to be late to class today. We know that these are true because of KCL. We have one input, one output, both of those cases. They're all in series. They all have equivalent currents, okay? I'm looking at this one. They're all in series, equivalent currents. So we're good there, equivalent currents. Now what we also know is that REQ2 extends between node 3 and node 4, which is the same as R3 and R4. If we find out what the voltage is across REQ2, we know what the voltage is between nodes 3 and 4. If we know what the voltage is between nodes 3 and 4, we know what the voltage is across these components. If we know what the voltage is across R4, we can find the current. Okay? So, V REQ2 is equal to I REQ2 times REQ2. We know that this is equal to 0.4 amps. We know that this is equal to 5 ohms, which means that the VREQ2 is equal to 2 volts. There are 2 volts between nodes 3 and 4. The equivalent resistance would experience a 2 volt difference. When we take those 2 resistors and we combine them into one, there are 2 volts across the ends. And that is true for both of these. There are 2 volts across the ends. If we were to do that for the other resistance, there are 2 volts, 0.4 times REQ1. REQ1 here was 20, it makes 8. So we know that there are 8 volts between 1 and 3, which makes sense because 8 plus 2 equals 10, which it should. Okay, so looking at this now, 8 volts between 1 and 3, we could figure out what the current is through REQ1. Well, it's 0.4, which again, if you bring this back in here, it's 0.4 amps flowing through components in series. We already knew that. But that's how you would solve R1, R2. To solve for now R4, we know what the voltage is between 3 and 4. It's 2 volts. So VR4 is equal to IR4 times R4. We know what this is, we know what that is. We do not know what IR4 is. IR4 is equal to VR4 divided by R4, which is equal to 2 volts, divided by 10 ohms, which is equal to 0.2 amps, which kind of makes sense because we have 0.4 amps coming in to node 3, 0.4 amps going across. These two resistances are the same, so it's going to be half of the resistance coming through. Okay, 0.4 divided by 2 is 0.2. It means there's 0.2 amps going through here, 0.2 amps going through here. Okay, now that we know the current, PR4 is equal to VR4 times IR4. So that's lowercase I, which is equal to 2 volts times 0.2 amps, which is equal to 0.4 watts. And that's the solution. Okay. I have homework that I will be posting online. Because we missed a day this week and because I'm posting the homework late, I'm not going to be giving as much as I would. In fact, I think I'm going to give you a quiz that has 1 question on it. And yeah, I'll give you free points on the quiz. So it won't be like 1 question, 10 points. No, it'll be a little bit easier. Your quiz question will be related to this material. So if you need to, you can ask me questions on Tuesday. Don't submit your quiz answer until you feel confident about it, because you don't get a second try. Okay? Your reading assignments and your homework assignments will be due Tuesday. Hand them in on Canvas. Make sure they're on engineering paper. If you need engineering paper, I have engineering paper for sale. $6 a ream. Okay. All right, I'll see you Tuesday.